Assalamu alaikum and a very wonderful morning to everyone. Okay, this morning we're going to look at the design pad which is given by the GEL03 on soil consolidation. Let's discuss this very detailed. Now there are a total of, let's see over here, 15 problems on soil consolidation. Let's go on one by one. So this is the first geotechnical engineering design pad given by C1. Okay, you need to write your particular details here. Okay, you have one spot here and also one spot here, the date that you did this design pad. Okay, again, I would like to stress, in any geotechnical design pad you would like to have three main aspects, which is first the aspect of specification, second is required, and lastly on your solution. So make sure you understand all of these three aspects before you can come up with a decision making in geotechnical engineering. Right, let's look at aspect number one, specification. Now a square rigid footing, which is a square 3 by 3 meter, is resting on a clay deposit. Now you'll have a foundation engineering over here and also your soil materials, which falls under soil mechanics or geotechnical engineering. B, the footing is to cater a load of 1800 kilonewton. So now you have a loading. C, the undrained elastic modulus of clay is 40 MPa, the first property of the soil. And lastly, the Poisson's ratio of the clay is assumed 0.5. This is from the structure, foundation, you have your loading, and then you're going to come with your soil properties. So everything is related. That's why you need to know all the studies related to soil to move on with this type of solution. Now what is required? The expected immediate settlement beneath the center of the footing. So the keyword is immediate settlement, and the solution, just go straight to the formulation given in your notes, which is equation C1, and just replace this accordingly. So if you look at the hint, okay, so this is the solution, and in the end your immediate settlement is 9.2 mm. Now let's look at GEDP number C2. Now this is on consolidation test. Alright, now the specification from laboratory is given. So you're dealing with clayey soil, so it was obtained from field and it is subjected to laboratory consolidation tests, and the result is as follows. You have your diameter, initial height of specimen, specific gravity, dry mass of specimen, and you are also given a pressure versus deformation dial readings. So the pressure versus deformation dial readings are given in table C4. So you have your pressure over here, the related initial deformation, which is 0 every time, and then the deformation dial reading, okay, representing 100% primary consolidation. And what is required? Initial void ratio, and of course the E log P curve. The solution. To calculate the initial void ratio, you just follow these steps accordingly. 1, 2, 3, and 4. By using simple soil mechanics formulation, you'll be able to calculate the initial void ratio. So in the end, the initial is given as 1.248. Okay, but you have to take care of all the units here. Okay, make sure everything is correct, and then you can proceed beautifully in finding initial void ratio, E 0. So the number 2, the E log P curve. Now, to develop this curve, the height solid in the specimen must be calculated. So there's going to be a changes in the height. So again, by using simple approach from solid mechanics formulation, you relate the height, the volume, and also the area. Okay, and every time the pressure occurs, you need to calculate the difference of thickness in order to get the E log P curve. Okay, so this is a summarization of the table. Start off with various pressure. You have initial deformation reading, deformation dial reading, and the changes of thickness. This is what you calculated. Okay, each of these pressure will represent the changes in thickness. Okay, so try to make a sense here. When pressure is increasing, okay, the change in thickness will also increase. Okay, very good. And also the change in void ratio will also change. You start off with 0 and then you get 0.56 for 100 kilopascal. Okay, and you can easily find the last column here, which is your void ratio. Okay, so based on this table, you'll be able to plot this void ratio versus logarithm of pressure. So y is the void ratio, and on the x-axis is your pressure. So you have 1, 2, 3, 4, 5, 6 data for this chart. Okay, so that's all for the GEDP number 2. Now let's go for GEDP number 3, where you have more information. So additional test results from the tests on clay soil is presented in previous problem. So you're going to use the same information, but in addition, the specimen was drained on both top and bottom during the test. So there's a flow of liquid up and below. Okay, and you're given with additional information of pressure versus information dial readings and time for 50% consolidation. So again, you have your pressure, initial height of the specimen, the deformation reading at 50%, and the time for 50% consolidation. So this is what given to you, calculated from laboratory works. And the required is CV log P curve, coefficient of consolidation with pressure. To start off, you need to know your thickness of specimen. So please calculate this accordingly, take care of the units. Now, the unique feature here is that because the specimen was drained on both top and bottom, half the thickness of the specimen must be used for H in equation C2. Okay, so you have two cases where the condition where you have the liquid movement top and bottom, okay, and you have to take this as the value, H divided by 2, and another case where H is impermeable, so there's no movement of water, or only one movement, so the H is different. But for in this case, you're taking H divided by 2. Okay, let's calculate for the 25 kilonewton meter square pressure. The value of T50 is given to be 8.2 minutes. Okay, and when you substitute this in the formula, you'll get your coefficient of consolidation as 3.81 multiplied by multiply with 10 to the power of negative 4 centimeters square per seconds. Okay, you can repeat this using the same method for the rest of the pressure. So this is a summarization of the computed coefficient of consolidation with pressure related. So you have your pressure here. So this is a step-by-step process. Okay, and you have your coefficient of consolidation in the end. So pressure with your CV over here. And then you can easily plot the graph. So on the y-axis is your CV, coefficient of consolidation, and on the x-axis is your pressure. So you have 1, 2, 3, 4, 5, 6 data for this problem. Now this is additional information. Now figure below is a relationship from which approximate values of the coefficient of consolidation as a function of liquid limit for different soil types can be noted. So this is published by US Department of the Navy in 1971. They did a lot of tests and they relate the coefficient of consolidation with the liquid limit. And they also have established a value that you can choose whenever you have information such as liquid limit. You can straight away get your coefficient consolidation. Okay, but you have to take care that different type of soil will have different type of chart. So in this case, 3 lines is given here. The first is the remolded samples and the undisturbed samples. Okay, 2 different types of sampling. And then this is the main important one, which is the range of recompression lies above this limit. Okay, you can do your own. You can have your solve from site and establish this chart. Now let's look at C4. So you're going to move to another chapter, normally consolidated clay. Number 1, specification is given as a visual. So a soil profile is presented here. Okay, so let's understand this properly. So you have your ground layer on top of here at the elevation of 86.5 meter and a water table below 2.5 meter from the ground level. And please note all the elevation level for each of the layer. Okay, so you have sand and gravel on top, a second layer, again sand and gravel, and then the clay. And what is required? The effective overburden pressure at mid-height of the compressible clay layer. Okay, which one is this one? Solution. The elevation of the mid-height of the clay layer is 78 plus 71 divided by 2. So it gives you the mid-height. So it's calculated as 74.5 meter. And then by using a simple overburden, effective overburden pressure formulation, you replace all the parameters accordingly and make sure when there's a water table, you need to minus off the unit weight of water and take care of each of this thickness. Okay, and in the end, the effective overburden pressure is calculated as 151.84 kPa. Okay, let's move on to problem number 5, C5. This is on field consolidation line. Okay, let's change this to highlighter. Okay, better. Specification: when the total pressure acting at mid-height of a consolidating layer is 200 kN per meter square, the corresponding void ratio of clay is 0.98. So that's first information. Second, when it's 500 kN per meter square, the void ratio is 0.81. So does it make sense? When the pressure increases, the value of void ratio decreases. So try to make a relationship. And what is required? is basically what's the void ratio at 1000 kilonewton per meter square. From here you can just make a simple understanding of math. Let's say 200 is equals to 0.98, okay, and then it's given 500, so it's 0.81. So how are you going to calculate for 1000? So of course the value is decreasing. Okay, so that's the simple concept to understand. So the void ratio of the clay at 1000 kilonewton per meter square. The solution, so a formula is given in your notes. Refer to equation C4. Okay, and substitute all the parameters accordingly. So if you look at the hint, the void ratio related to 1000 kilonewton meter square can be calculated and is 0.427. Oh, sorry, it's not 0.27. You have to calculate from this formulation. Okay. Now let's look at problem number 6. This is the shortest formulation. A normally consolidated clay has a liquid limit of 51%. Estimate compression index. Use a simple formulation in your notes, equation C5. Replace this accordingly, basically your LL, and then you get your estimated compression index calculated as 0.369. This is problem number 7. Let's look at specification. A compressible normally consolidated clay layer is 7.4 meter thick and has initial void ratio in situ of 0.988. Consolidation tests and consequent computations indicate that the void ratio of the clay layer corresponding to the total pressure acting at mid-height of the consolidating clay layer after construction of a building is 0.942. Total expected primary consolidating settlement, which is your first stage. From equation C15, if you replace these parameters accordingly given in the problem, you're likely to get your primary consolidation settlement as 0.171 meter. Let's move forward. This is problem number 8. Under the scope of settlement of clay loads on clay due to primary consolidation. The specification as follows. A sample of normally consolidated clay was obtained by a Shelby tube. So this is one of the tube sample. From the mid-height of a compressible clay layer. The second item, a consolidation test was conducted. And it was found out that the natural void ratio of the clay existing in the field is 1.65. And of course you have your pressure relation with the void ratio as follows. Again, double check. If the pressure increase, the E will decrease. Now a footing is to be located 1.5 meter below ground level. The base of the square footing is a square, of course 3 by 3, and it exerts a total load of 25 kilonewton, which include column load, weight of footing, and weight of soil surcharge on the footing. So this one goes back to your chapter number. What chapter is this? Chapter number 2. Very good, which is on stress distribution. And the required, from the given results of the consolidation test, prepare an E-log P curve and construct a field consolidation line assuming that point F is 0.4 initial void ratio. And the second item required is compute the total expected primary consolidation settlement for the clay layer. So this is a soil profile related to the problem. So you have a square footing here, ground elevation at different height, okay, and you have water table. So first layer of soil, second layer of soil. Now solution. First, you have to settle the curve. So how to settle this? Start off by calculating effective overburden pressure at mid-height of clay layer. So use a simple formulation. Okay. And you're likely to get effective overburden pressure as 106 kN per meter squared. Initial void ratio is given 1.65. And you assume field consolidation line is taking care of the 0.4 initial void ratio, which is 0.66. So when you plot the graph with this data over here, okay, the required was prepare the E log P curve and construct the field consolidation line. So this one, you can refer back to your notes, a step-by-step process, how to get A, okay? And you just need to show the 0.4 multiply with the initial void ratio line, which is this part, okay? So this one is a field consolidation line with this assumption on field, 0.4 initial void ratio, which is 0.669. Okay, so you show the curve and you show this line here. So that's the required one for the first item. Let's go to the second one. Compute the total expected primary consolidation settlement for the clay layer. Okay, so for the clay layer, you gotta go back to your stress distribution topic. So effective weight of excavation, you should know the top layer accommodate for 1.5 meter. So the effective weight of excavation is calculated as 30.15 kN per meter square. And the net consolidation pressure at base of footing is 248 kN per meter square. Okay. So when you have this loading, okay, please go back to chapter number 2, stress distribution. You have your loading calculated here. Okay, at the base of the footing, you have the properties of your footing, which is a square 1.5 by 1.5 meter. And then you use the appropriate formulation. In this case, is this one. Okay. And you need to calculate for the net consolidation pressure. So this is consolidation, not consideration. Okay. And finally, we come out with the pressure at mid-height of the clay layer, which is calculated as 130 kN per meter square. And use this value, put it in the graph, and you're likely to have 1.60. Okay, for your void ratio. So you have initial void ratio given as 1.6, void ratio 1.60 related to this pressure calculated, and the height is 4 meter. So if you substitute into the equation C15, okay, you can calculate your settlement due to primary consolidation as 7.5 centimeter. Let's move on to problem number 9. It's still in the same scope, the settlement of loads on clay due to primary consolidation. Okay, but here the total consolidation is 7.5 centimeter. Okay, the total settlement is given 7.5 centimeter, and the result from laboratory tests, the coefficient of consolidation is given for the clay sample 0.0212 centimeter square per minute for the pressure increment from 80 kPa to 160 kPa. Okay, and what is required? The time of primary consolidation settlement if the clay layer is underlain by A, basically a case where you have double drainage, and second, if you have single drainage. Okay. Now take you at 10% increment. So your percent of consolidation starts at 10% increment, 10, 20, 30, and so on. So you need to calculate for two type of case. The first case is A, and the second case is B. Double drainage and single drainage. use the respective formulation, but the difference is during the calculation of your height. Okay, for double drainage, just divide by 2. Okay, for single drainage, use as is H. Okay, from here, all the basic formulation can be obtained from laboratory sheets, and you're likely to calculate settlement for each of the respective percent of consolidation. 10% of consolidation will, after calculation, you'll get 0.75 centimeter of settlement. Okay, you're gonna do this repeatedly for the rest of the 10% increment. So that was 10%, is 20%, 30%, 40%, and so on. Okay, that's for the first case, which is double drainage, permeable sand and gravel, and second case, impermeable bedrock. The same steps, but you take H as is, the total H. You don't divide by 2. So when you have percent of consolidation 10%, you're calculating for the settlement, okay? Settlement value. So in the end, you're going to come up with table C8, double drainage, first case, and single drainage, second case. Okay. Percent of consolidation is here, 10%, 20%, until 100%. It relates to the consolidation settlement that you have calculated, and also the time for 2 cases. Okay. From here, you can come up with 2 data for this settlement log time curve. Okay, you have your settlement on the y-axis and your time in the x-axis. Okay, so make a difference between these two. Okay, okay, let's move on. So this is problem number 10. Specification. A 3-meter clay layer beneath a building is overlain by stratum of permeable sand and gravel, and it is underlain by impermeable bedrock. So 2 cases underlain. The total expected primary consolidation settlement for the clay layer due to the footing load is 6 centimeter. So the settlement is given, and the coefficient of consolidation is also given. What is required? How many years will it take for 90% of the total expected primary consolidation settlement to occur? Second, estimate the amount of primary consolidation settlement occurrence in 1 year. And lastly, how many years will it take for primary consolidation settlement for 2.5 meter to take place? This is just the rearrangement of problem number 9. So if you follow this step by step from problem number 9, so when I give a blank in one of the parameters, you just rearrange. Okay, so this is how you see for problem number 10. Okay, we're not going to be discussing this in detail, but basically you're just repeating things with a blank parameter. Now this is problem number 11. Still in the scope of settlement of loads on clay due to primary consolidation. Now, a foundation is to be constructed at a site. The soil profile is presented below. The base of the foundation is 3 meter by 6 meter. So now you're having a rectangular foundation, and it exerts a total of 54,000 kilonewton. Now you're having a load. Initial void ratio in situ is 1.38. The compressive index is given as 0.68. And what is required? The primary consolidation settlement. Of course, you're going to end up with a formulation from this chapter. So understand this profile. You have elevation at 200 meter for the ground surface. You have your footing here of a rectangular section. And you have 2 layers, which is sand and gravel for the first layer and clay layer on the second layer. Now the solution. Firstly, calculate the present effective consolidated pressure at the mid-height of the clay layer. So if, again, you have to take note, if there's a water table, you just have to minus the unit weight of water. This is basically repeating the previous problem. Okay. Again, effective weight of excavation need to be calculated, and the main finding is the net consolidated pressure at the foundation base in order to move on with the settlement calculation. So approximately 235.3 kilonewton meter square is taken into the stress distribution approach. Okay, so again, you're repeating the same thing, but this one is of rectangular approach. And having all these parameters, you can calculate for your settlement using this equation. And finally, your settlement is calculated as 0.2121 meter. 0.212 meter. Let's move on. Problem number 12. Okay, same information given from problem C11, sorry, and the computed settlement of 0.21 meter is used. So we're going to use the same output, and the coefficient of consolidation is given as this value. What is required? How long will it take for half the expected consolidation settlement to take place of the clay layer when underlain by the first case and second case? Okay, basically the change of your consolidation percent to 50%. Okay, again, the same approach is repeated, and that's how you calculate for this problem number 12. Now let's look at a new topic on the scope of settlement of loads on clay due to secondary compression. Now we're going to go on secondary compression. The specification given as follows: a foundation is to be built underlain by a highly compressible clay layer of 5 meter thick. A clay layer's natural water is 80% water content, and the primary consolidation is estimated to be complete in 10 years. Okay. What is required? Secondary compression settlement expected to occur from 10 to 50 years after the construction of the foundation. Basically using the formulation with the respected information given here. Okay, so you have this is given, and the time is given also, and in the end you can calculate by using this basic secondary compression formulation from your note C25, and you're going to get your secondary compression as 0.052 meter. This is secondary consolidation, sorry, not compression. Okay, so that was problem number 13. Now let's move on to the last problem in C14. Okay, basically using the result from C13. Okay, the same information is extracted from C13. Now assume that primary consolidation will be completed in 5 years and the natural water content is 50%. What is required? Estimate secondary compression settlement for 50 years after construction. So by using figure C22 with a natural content of 50%, hence you get this. Okay, and take note of the rest of the parameters given, and you'll get your secondary consolidation settlement as 0.033 meter. Oh, this is the last, problem 15. This is on the scope of settlement of loads on sand. Previously was all on clay, now is the first problem on sand. Specification: a square footing of 3 by 3 meter located 1.5 meter below ground level is to be constructed on sand with a unit weight of 18.30 kilonewton per meter square. The arithmetic mean of the SPTN value measured within the zone of influence is 30. Well, please take note of N from an SPT. What is the allowable salt pressure for a settlement of 25 mm? Now, the solution. Assume that the foundation contact pressure is greater than the pre-construction effective overburden pressure at the foundation base, in which equation C28 applies. So this one is from your notes. Again, thanks to Marisa for pointing out this. Okay, so this is the solution. So you have all of this identified from the specification. Write this accordingly. S as 16 mm, your B 3 meter, N is 30, and then you calculate for your P0, which is 27.45 kilonewton per meter square. Okay, follow this step by step. Okay, okay, so you have this after substituting all the parameters. So therefore, your Q is 501 kilonewton meter square. Check the assumption that Q is more than P0, so it's okay. So use equation C28 because you have made a right assumption in the beginning. As an alternative solution, using figure C26 with B 3 meter and N 30, Q is 30 kilonewton per meter square. Okay, and because Q is more than P0, use equation C33. So in the end, whatever is being required, which is allowable salt pressure for a settlement of 25 mm, can be calculated. So two approach here. One is a simple formulation, and second is another equation. Okay, so that's how you calculate allowable salt pressure for settlement of 25 mm. So that's all about it. Thank you very much.